Welcome to AP Statistics. In this video, we're going to talk about experimental design in a flash. All right, so really, studies are done to identify relationships. When you see, a research study was done here, a research study was done there, usually they're trying to establish a relationship between two variables. All right, they're trying to figure out, does an explanatory variable have some type of impact on response variable? We don't want any extraneous or confounding variables getting in our way. We want to really know, does this one variable have an impact on this second variable? Now, there are two types of ways to conduct this type of study. One is an observational study and one is an experimental study. Now, the number one difference between these two different types of study is in an experiment, you as a researcher have direct control of the treatments given to the subjects in hopes of showing a cause and effect relationship. That's the goal, right? An experiment, you give. You tell them what to do. That's the primary difference. Now, an observational study is done because, most people would say, well, then why don't we always do experimental studies? Well, observational studies, if direct control is made impossible due to ethical or logistical constraints, then observational study is great to do. I mean, sometimes you can't make people do certain things, or it's just unethical to make them do something, or, the logistical constraints of trying to organize an experiment sometimes can be very difficult. So an observational study is when you as a researcher, just observe. You sit back and observe. You're allowed to ask questions. You're allowed to, ask questions before, ask questions after, but you don't make people do anything. You just observe what they do. Now, observational studies are great. They are definitely used a lot to show relationships and associations between two variables, but with too many possible confounding variables not controlled for, because it's not an experiment, we cannot use that word cause. So we cannot say at the end of an observational study, X causes Y. We could just say that there is a strong relationship between X and Y, or there's a tendency that as X changes, Y changes, but we can't use that word cause. All right, so let's just dive into an experimental study because this is where the thick of the video lies. So we want to show an explanatory variable causes an impact in a response variable. To make sure this happens and to be able to say, hey, this causes this, we have to conduct an experiment, and we have to make sure that it hinges on four key pillars: comparison, random assignment, control, and replication. Let's just run through them really quickly. So comparison is at the very minimum, you have to have two or more treatment groups, okay? You cannot have everybody getting the same thing. So let's just do an example here where we have three different groups. We have people getting treatment 1, treatment 2, and treatment 3. You got to have something to compare to. You cannot just have one treatment group where everybody gets the same thing because you won't know that it's better or worse than something else. Now, a lot of people hear about this word called a control group. A control group would be technically a group that gets nothing. You could add a fourth group if needed, or maybe you only have two and you want to, but you don't, as long as you have two groups, you don't need a control group. But, the purpose of a control group, which, could just be your group 4, is maybe you find out that taking nothing or doing nothing, or being told nothing, is actually better than doing something else. And you need a control group to kind of get a baseline to kind of compare your data to. So sometimes control groups are good. But listen, if your study is purely, does toothpaste 1 make your teeth whiter than toothpaste 2? Well, if that's all you care about, then you don't need a control group that gets nothing. As long as at minimum, you have two groups to compare. All right, the next major thing is random assignment. So if you have your subjects, those are the people or objects involved in your experiment, who goes into treatment 1? Who goes into treatment 2? Who goes into treatment 3? Who goes into a fourth or a control group? That must be done randomly. Those subjects must be put into those groups randomly. They cannot decide. If they decide, we have an instant confounding variable of self-selection or motivation because they pick the group that they maybe like best. So how do you do that? Well, if you got 100 subjects, everybody gets a number, no repeats or no numbers nobody has. First 25 numbers selected with your random number generator go into group 1. Next 25, group 2. The third group of 25 goes into group 3, and the remaining subjects go into your control group or group 4, whatever the heck you want to call it. Got to be random. Pretty simple. Not hard at all, right? Here is the big goal, though, right? Randomness sounds fun. It sounds awesome, but there's a really important reason why. We need this group, this group, this group, and this group to all be very similar. Now, what do I mean by that? What I mean is that we want them to be similar between, different within. So what do I mean by that? Okay, well, this is where it gets a little bit tricky, so bear with me. We want these groups to all be similar. We want the only thing different about these groups to be what I give them. That should be the only thing that's different about them. But we want representation, right? If we want to show something works, we want to show that it works for a wide variety of people. So we want the subjects in group 1 to be a wide variety. Boys, girls, rich, young, this, that, right? But we want the same thing for group 2. We want the same thing for group 3. We want the same thing for the group 4. We want all of the groups to be very different within, which makes them similar between. That way, the only difference between these groups is what I give them. You don't want somebody saying, well, all the people in group 1 were young people. All the people in group 3 were old people. Nope, they were young and old in both groups. All the people in the control group are girls. All the people in the group 2 were boys. No. There were boys and girls in every group. And if you do it randomly, that should naturally happen. Getting these, it's like a salt shaker, right? I got my subjects in a salt shaker. I'm going to sprinkle them into all 4 groups, completely random, mixing it up. And again, that's a good thing. All right, now the third pillar is control. Now, a lot of kids think that that means you got to have a control group. No, I already talked about what a control group is. When I mentioned control as a pillar, that means you keeping as many variables the same as possible. So again, all 4 groups should be treated the same. They all take a pill at the same time with a glass of water. They all do it for 12 weeks. Whatever you're giving them needs to be the same. Obviously, the only difference you want to be the treatment that you give them. But other than that, everybody should be treated the same. Now, one thing you could do is, well, okay, let's have a lot of control. Let's use all men in their 30s. All 4 groups are men in their 30s. That way, there is no, we have control, right? We're keeping everything very, very similar. Okay, that may sound great. But then the results of your experiment can only be said true for men in their 30s. So we want to use a good mix of people, right? And the random assignment will help create that. But the control is making sure that everybody's treated equally, right? We want a level playing field for all the participants, again, other than the treatment I give them. So another example of this is single and double blind, right? When you're working with humans, you would prefer that your subjects are all blinded. They don't know what they're getting. Maybe you could give them a fake pill, or maybe the pills all look the same, or who knows. So if you could blind them, that takes away a form of bias, because that way they don't know what they're getting and they don't have any expectations because of that. So that's a good thing. Now, sometimes you're in a situation where you can't blind them. Like, they obviously know what they're getting. Okay, it is what it is. But we could also blind the evaluators, the people that are going to judge them at the beginning or evaluate them at the end. Those people should be bias-free as well, so they should be blinded to not knowing what treatment each subject was getting. So if you could blind both the subjects and the evaluators, that's double blind. If you can only blind one group, it's called single blind. But regardless, blinding is a form of control because you're trying to keep everybody the same, other than what you give them. Even using a placebo. See, when you involve humans, you have something called the placebo effect. The moment you give a human something, yay, they may feel excitement that they're a part of the experiment, or the moment you take it away, they're going to feel all upset that you didn't give them anything. So the placebo effect is the fact that when you're involved in an experiment, you think something good might happen to you. You cannot actually take that away. You cannot eliminate the placebo effect, but what you can do is give everybody something, and that's what a placebo is used for. So a placebo isn't always necessary, but if it's used, that's a form of control. You're trying to maintain the placebo effect for all subjects. Replication is the idea that the more subjects you use, the more value you're going to have in results. If I only put 2 people in all of these groups, all right, 2's not bad, it's better than 1, but you're not going to really see any major differences. Or if you do, it could be because of a lot of other extraneous variables. But if I have 200 people in every one of these groups, then if I see, let's say, group 2 significantly better than all the groups, well, if that's true for 200 people, that's a lot stronger evidence than it's only true for 2 people. So replication is really this idea that stronger results are going to come from more people. Heck, if I can do 2,000 people in every group, I'm going to have even more stronger results to go on. All right. Now, all 4 of those pillars have to be there, but there are 3 different ways that you could design an experiment. But again, every one of these designs needs to lead us to 4 just because of my last example, but you have to have 2 or more groups, that are 2 or more treatments, 2 more groups of people getting something, 2 more things to compare, right? So again, if I'm going to have 4 things, based on the example I was working with a minute ago, all of these design types will lead to that. It's just how we get there. So you completely randomized is actually what I've already said. Got all of your subjects, who goes into what group, completely random. Everybody gets a number, first 25 go to 1, next 25 2, next 25 3, last 25 4 if you have 100 subjects. A randomized block design is when there is a confounding variable that you are way too worried about. So maybe you're really worried about a certain variable and you don't want all of that one variable going into treatment 1, maybe by mistake or because of pure randomness. So what you do is you block. So you first create groups of people based on that confounding variable that's important to you. Then in each block, you give out all 4 treatments. So everybody in block 1 gets a treatment. Randomly, of course. Some get 1, some get 2, some get 3, some get 4. And then the same thing is going to be said for block 2, some 2, some 1, some 3, some 4, and so forth. Now, I know that I'm explaining that in a way that might be a little bit confusing. I'm going to clear it up in a couple moments with a nice example. But again, if you have a block design, the idea is that it's kind of like stratifying, right? Like you just are like too concerned about this one variable. And if you do it random, maybe, like for example, gender. Maybe all the boys go into treatment 1. Well, that could be a problem because now gender is confounded with your results. So what you do is you say, okay, I'm going to have 2 blocks, gender, boys, another gender, girls. And I'm going to have in the gender boy block all 4 treatments given. Same with the girls. What that's going to guarantee is that in each of these groups, you have both boys and girls. I'll make that a little bit more clear in a little bit. A matched pair design is when you pair people together. So the only drawback to a matched pair design is you're only allowed to have 2 treatments. If you have 3 treatments, there's no such thing as a matched trio design. Okay, matched pair design. So what you do is you match people together because they have a lot of similar characteristics. They're very, very similar. So these 2 people are very, very similar. And in each of these groups of 2 people are very, very similar. Then in each pair, somebody gets 1, somebody gets 2. Selected randomly. In this pair, somebody gets 1, somebody gets 2. Randomly. In this pair, somebody 1, somebody 2. Randomly. In this pair, somebody 1, somebody 2. Randomly. Just realizing that my lines look absolutely terrible. But anyway, you get my point. Is that in each pair, both treatments are given. So again, what you're purposely doing is mixing up your treatment groups. Because remember, these 2 people are very, very similar. One of them in 1, one of them in 2. These 2 people are very similar. One of them in 1, one of them in 2. These 2 people are very similar. One of them in 1, one of them in 2. What this actually creates is 2 treatment groups that are very, very different within, similar between. All right. Sometimes explaining the designs without an example can be a little bit tricky, so let me throw out an example with you to end the video. Researchers want to show that a new pill containing chondroitin can help elderly people improve osteoporosis. All right, so elderly people is my population. Maybe I get a bunch of elderly people as my subjects. They're all elderly people, and they all struggle with osteoporosis. That's my population of interest. All right. So I have people that want to go into the treatment group that actually get my new pill of chondroitin. And then maybe I have a group, and because of control, I'm going to give them a placebo. So they're a control group, and I want to make them think they're getting something, so I'm going to give them a placebo. That way everybody goes home getting something. I'm going to blind them. That way the pills are all look-alike. They don't know what they're getting. The evaluators are going to do the judging at the end. They're blinded. They don't know, as they're evaluating the subjects. They don't know who got what. So here's what I'm going to do. Completely random. However many subjects I have, everybody gets a number. Randomly, half go here, half go here. If you think about it, that should give a nice mix of people. I'm probably going to get all different types of people in this group, all different types of people in this group, which means within each group, they're very different. So that means between, they're both similar in the fact that they're different, and I can compare that at the end. That's completely randomized design. Now, if you're like, well, wait a minute. I know that how much you exercise matters. How much you exercise could directly help or maybe hurt your osteoporosis. And that means there's another variable that could cause a change in the response besides the treatment I'm giving them. So this is where maybe you'd set up a block. You'd say, okay, I'm going to have a block of people that exercise a lot. I'm going to have a block of people that exercise a little. And maybe I find this out through a survey or something, right? And then I have a block of people that don't exercise at all, so no exercise. Then, in the exercise group, I'm going to randomly give my new pill to half and my placebo to half. In this group of those that exercise a little, new pill to half, placebo to half. In my group that doesn't exercise at all, new pill to half, placebo to half. Okay? So now, at the end of the day, I have 2 treatment groups. I still have 2 groups. I got a group getting my pill. I got a group getting the placebo. But because I blocked first, I'm guaranteeing that this pill group has some that exercise a little, and some that don't exercise at all. I'm guaranteeing all different types in this group, and same thing with the placebo group. So blocking ensures that that variable is split up. If I did it completely random, there is a possibility, probably very unlikely, but there is a possibility that everybody that exercised ends up in one group, maybe taking the pill. Now I have a confounding variable. Did they get better because they exercised, or did they get better because they took the pill? If I'm really concerned about that important variable, I block. So again, why am I blocking? Because I want to reduce the variation for what I'm measuring. I want a nice mix because my population is a nice mix. So I want a nice mix of people in both groups. That way I'm actually eliminating exercise as a variable. So bringing exercise to the front by blocking eliminates it as a confounding variable. Because I'm purposely putting people that exercise a lot, a little, and none in both groups guaranteed. All right, last different technique is the matched pair. Now, you can only do this with 2 treatments. So I do have 2 treatments, placebo and the new pill. So who would I pair together? Maybe I'd pair together people that are both men, both the same age, both current levels of osteoporosis, and both exercising the same amount. This pair, both females, same age, same osteoporosis, same level of exercise. So I create a bunch of pairs for my subjects. Then, in each pair, one of them goes into my pill group, one of them goes into my placebo group, and that would be done randomly, of course. So again, in this pair, 1 here, 1 here. In this pair, 1 here, 1 here. In this pair, 1 here, 1 here. So what I'm doing is, for example, I'm putting a man in both groups. I'm putting a person with the same level of osteoporosis in both groups. I'm putting a person that exercises the same amount in both groups. I'm putting somebody that's the same age in both groups. And then I'm doing it again and again and again and again and again and again and again. So I should have different people in both groups. So this group taking the pill is going to be filled with men of different ages, men of different osteoporosis, women of different ages, women of different osteoporosis, women and men of different exercise habits. But guess what? Their similar pair is going to be in the placebo group too. So once again, I'm really forcing my 2 groups to still be random, but they're very, very different within. I want each group to be different within, which makes them similar between. So now the only difference is, did you take the pill or did you take the placebo? There are men in both groups. That's not a confounding variable. There's women in both groups. That's not a confounding variable. People that exercise a lot in both groups, a little in both groups, have high levels of osteoporosis, have low levels of osteoporosis in both groups. None of those things are confounding variables anymore because they're in both groups. So that's the advantage of doing a matched pair design. So that's a quick rundown of experimental design. I know it's fast and furious, but it's still about 19 minutes long here. But it's really important for you to hear all those kind of facts, understand how they all kind of come together. So hopefully it was a nice quick review for you.